The hip joint serves as a cornerstone of human independence, enabling fluid movement and stability in essential daily activities. From walking and climbing stairs to sitting and standing, the hip provides crucial support and balance. Its flexibility and strength allows individuals to engage in many physical activities, from sports to routine tasks, giving a sense of autonomy and freedom. Due to modern advances in manufacturing and technology, humans are able to create biocompatible hip implants to mimic hip movement. In this video, we aim to explain the mechanics, biological importance, along with the material selection, design, and manufacturing processes that go into developing a hip implant.
The hip joint serves as the link between the femur and the pelvis. It is designed as a ball and socket structure, with the femoral head acting as the ball and the acetabulum forming the socket. The femoral head, neck, and acetabulum are the main components to focus on in order to understand the design behind hip replacements, which we'll get into later. The ball and socket design that we previously talked about allows for a three-dimensional range of motion, which includes flexion, extension, and then an internal rotation, along with an external rotation. Finally, it has an abduction and then an adduction. After having looked at the hip's movement and function, it's important to talk about what kind of forces act on the hip joint and how its general structure plays a role. So on this diagram, you can see a drawing of a hip joint with the body weight force acting downwards at the center of the hip, along with another force that comes from the hip abductors. Now, these hip abductor muscles try to balance the hip joint and straighten everything out. Now, when you add these two forces together, you get a third reactionary force that stems at the top of the femoral head and acts opposite their direction. When you put all these three forces together, you get a compressive effect that particularly affects the femoral neck area. Now, we'll get more into how that looks like in the finite element analysis portion of it. We could take a closer look into how the pressure is distributed using a finite element analysis. As you can see, most of the load bared is located on the lower half of the femoral neck, which makes sense given the shape of the joint and how the force acts on it. This new finite element analysis compares a normal hip joint to one that suffers from osteoarthritis, which is one of the most common reasons behind needing a hip replacement. The energy density is located throughout the whole neck and makes its way onto the femoral head. This affects the hip negatively, given that it was not designed for such a distribution.
As a person ages, the cartilage in their hips can wear and begin to break down, resulting in painful bone-on-bone contact, commonly referred to as osteoarthritis. This kind of intense wear causes the body to grow bone spurs on the femoral head and acetabulum, which only causes more pain as time goes on. It is estimated that worldwide, over 10% of men and 18% of women over the age of 60 suffer from these painful symptoms. Since both the ball and the socket part of the hip are damaged, the most common treatment for a patient is to have both pieces replaced. In other words, a total hip replacement, where the femoral head, acetabulum, and remaining cartilage are replaced with an artificial substitute. Today, over 4.7 million Americans currently live with a total hip replacement.
Now let's talk about material choice when designing hip implants. The ultimate focus when designing any component that will eventually be placed in the body is designing for biocompatibility. What does this mean for the manufacturer? It means using materials and elements that mesh well with existing body parts and do not end up causing infection or pain in the patient. After decades of research, it's been found that one of the best materials for designing orthopedic implants are titanium alloys. These alloys are light, machinable, strong, and corrosion resistant compared to iron and aluminum alloys. Titanium makes up most of the hip replacement, with the only non-titanium pieces being buffers between hip movements. Let's take a look at some of the actual components of a hip replacement. The first titanium piece is the acetabular gut. This acts as a socket for the ball and socket joint of the hip and will directly mount into the pelvis. This primitive socket is lined with a high-grade polyethylene liner or insert. Polyethylene, a known biocompatible plastic, is best for this as it greatly lowers the friction between the ball and socket while providing great bacterial resistance. reducing the risk of infection and lowering recovery time. The cup is connected with the socket part of this assembly, the femoral head, and the stem. While the head is what directly attaches to the other side of the socket, the stem allows replacement to be grafted into the bone. The femoral head is most commonly 32 or 36 millimeters in diameter, allowing biomedical device companies to lower their manufacturing costs by making fewer sizes. The head is screwed into the femoral stem, which is eventually grafted into the patient's femur. It is important to note that all material areas being grafted into bone have to be treated to help them better latch onto the bone. These components and their design decisions from years of research all help to reduce patient recovery time, reduce the risk of infection, and help hip implant producers optimize their manufacturing processes.
Next, we're going to look at the manufacturing processes that are required in order to make the 4 different components of the hip replacement implant. The production of the implant begins through research and development, where a 3D model of the entire assembly is created, which can then be prototyped using 3D printing. After refining the design, each component of the hip replacement, which includes the femoral stem, acetabular cup, femoral head, and polyethylene liner, can be manufactured. To create the femoral stem, rods of titanium are first inspected to ensure that there are no defects. Next, the rods are cut into billets and coated with lubricant to help prevent friction between the rod and future dies. The rods are preheated in an induction heater to prepare them for forging. Then, each rod is sent to a forging press, where the rod is flattened and deformed into the shape of the stem. Afterward, the stem is annealed, allowing it to cool slowly, reducing internal stresses in the material. The stem undergoes CNC milling and taper turning to remove any unnecessary material and minimize sharp edges. The stem receives surface treatment through grinding and polishing to ensure smoothness. The stem then is coated with titanium plasma spray, hydroxyapatite or HA, and titanium beads. The beads serve as a connection for the bone to grow to the implant itself. Finally, the stem is sintered, allowing the beads to heat up and properly adhere to the stem. To create the acetabular cup, a similar process to the femoral stem is required. Like before, a titanium billet is cut, lubricated, and preheated with the intention of being forged. At the forging press, the heated titanium is first formed into a spherical shape. Immediately after, the titanium piece is forged again, this time with the center being pressed inward where the die has a smaller diameter than the piece, creating a hollow dome shape. Once cooled and checked for the correct thickness, the titanium dome undergoes CNC turning to enhance its revolved profile, as well as to create junctions inside the dome where the polyethylene liner can easily fit into. Like before with the stem, the acetabular cup is coated with titanium plasma spray and HA, enhancing bone growth. The femoral head, which attaches to the top of the stem, is formed like the acetabular cup, where preheated titanium is forged into a hollow spherical shape that fits on top of the stem. After cooling, the ball-shaped head is polished and ready to be attached to the stem. Finally, to create the acetabular or polyethylene liner, polyethylene undergoes CNC turning, where the material is formed into a hollow dome matching the inner diameter of the acetabular cup. The liner is then deburred, meaning that it is smoothened and has any rough edges removed, ensuring a proper fit to the acetabular cup. Once all 4 components of the implant are formed, they are then cleaned and ready for assembly. The femoral head is screwed onto the femoral stem, and the lined acetabular cup can be pressed onto the head. Now the implant is ready for the patient.
We hope this video gave you some insight into the mechanics, biological importance, design, and manufacturing of hip implants, and helps you understand the complex systems and considerations made throughout this process.